Awesome. Cool, should be live. How are you guys doing this morning? Let me get this set up a little bit. You guys hearing me all right this morning? Cool. Let me get my screen up here. Here we go. Awesome. Let me go ping the Discord, and then we'll give people maybe a minute or two to trickle in here, and then we'll get started. Hey there, Kat, Sebas, Stefan, Connor. Doing OSRS fishing while watching the stream? What does that even mean? What's OSRS fishing? Oh, old school RuneScape. Gotcha. Yeah, so I'm still trying to figure out this whole YouTube thing. Check this out. I figured out I can make a goal. If I get one super chat in this stream, I'll be happy. See? So that's our goal. Not too worried about it though. What else did I figure out? Oh yeah, I got access to like all this music. Not sure what I'll use that for yet. Maybe my like monthly. Because I don't have music in streams, but I might do music in my monthly ones. Which I still need to make for the month of April. There's something else cool I found. Oh yeah, I'm like about to hit the next. Oh wait, maybe I already did. Oh no, here we go. See? As soon as I hit that, then I hit like the next tier. So, it's pretty fun. Not sure why I just showed all that, but. Alright, we'll start. Who's ready? We're gonna do some more C, right? So let me find my book. All right, today's the type system. Just what we wanted. The type system. Cool, we'll just jump right in, no? The notion of type. Morning, Kaya. Doing anything in Lovely later? The stream is right in the middle of the work morning. Seos, no way. Thank you so much. $2? That hit my goal. I'm happy. See the smile? Seriously, thank you, man. Okay. Jose, yeah, doing any Lovely later? Well, I need to check my calendar. Let me check my calendar. So I have something at 8, and then I have a guitar lesson at 10. I could probably make something work. Although, I should probably get some of my other work done. Yeah, I'll say I probably won't be able to get to a Lovely stream today. Obviously, I'll let you guys know if that changes, but it's not looking like it's gonna work out super well this morning or this day. But tomorrow should be good. I'm not sure yet though. That might change though. I might change my mind. It's just sometimes I'm not sure what to prioritize. All right, but let's do some C for now while we can. Have a nice day at work, Jose. Thank you. All right, the notion of types is one of the key ones. A type is essentially a tag assigned to a data entity. Every data transformation is defined for specific data types, which ensures their correctness. You would not want to add the amount of active Reddit users to the average temperature at noon in Sahara, because it makes no sense. Correct. This chapter will study the C type system in depth. Basic type system of C. That just reminded me of this cool Swift library. But anyway, which is something I kind of want to be built into Lovely, but we'll hold off on that for now. All types in C fall into one of these categories. Predefined numeric types, int, char, float, etc. Arrays, multiple elements of the same type occupying consequent memory cells. Pointers, which are essentially the cells storing other cells' addresses. The pointer type encodes this type of cell it is pointing to. A particular case of pointers are function pointers. Structures, which are packs of data of different types. For example, a structure can store an integer and a floating point number. Each of the data elements has its own name. Enumerations, which are essentially integers, take one of explicitly defined values. Each of these values has a symbolic name to refer to. Functional types. Constant types built on top of some other type and making the data immutable. Type aliases for other types. Cool. You're starting with numeric type. The most basic C types are the numeric ones. They have different sizes and are either signed or unsigned. Because of a long and loosely controlled language evolution, their description may seem sometimes arcane and quite often very ad hoc. Following is a list of the basic types. Char can be signed and unsigned. What? What's a signed char? By default, it is usually, hold on one second. Okay, I'm back. I just got some golden glow tea delivered to my door. Alright, by default it is usually signed number, but it is not required by the language standard. This is confusing. Signed is just being able to be negative. Yeah. I just thought the chars were always used to represent chars, but maybe it's just used to represent 1 byte ints too, I guess. All right. Despite the name making a direct reference, right here, to the word character, this is an integer type. It should be treated as such. It is often used to store the ASCII code of character, but it can be used to store any 1 byte number. I'll check it out. Yep, 2's complement. A literal x and corresponds to an ASCII code of the character x. It is type is int, but it's safe to assign it to a variable type char. Okay. Let's use these single quotes for char stuff. Char number equals 5, char symbol code equals that, char null terminator equals that. Okay. Int is an integer number, can be signed and unsigned. It is signed by default. Can be aliased simply as signed. Signed int. Similar for unsigned. Okay. Can be short, 2 bytes, long, 4 bytes on 32-bit architecture, 8 bytes on Intel 64. Most compilers also support long, but up to C99 it was not part of standard. Other aliases: short int, signed short int. Oh geez. The size of int without modifiers varies depending on architecture. It was designed to be equal to machine word size. In the 16-bit area, the int was obviously 2 bytes. In 32-bit machines, it is 4 bytes. Unfortunately, this did not prevent programmers from relying on an int of size 4 in the era of 32-bit computing. Because of the large pool of software that would break if we change the size of int, its size is left untouched and remains 4 bytes. It is important to note that all integer literals have the int format by default. If we add suffixes l or ul, we will explicitly state that these numbers are of type long int or unsigned int. Sometimes it is of utter importance not to forget these suffixes. Consider an expression 1, this is some bit shift thing, 42. Its value is not 2 to the 42 as you might have thought. I wasn't thinking that, but okay. But 0. Why? The reason is that 1 is a literal of type int, which occupies 4 bytes and thus can vary from -2 to the 31 to 2 to the 31 minus 1. By shifting 1 to the left 48 times, we are moving the only bit set outside of integer format. Thus, the result is 0. However, if we do add a correct suffix, the answer will be more evident. An expression 1l. Gotcha. All right, long. In x64 architecture, it is the same as a long, except for Windows, where long is 4 bytes. Its size is 8 bytes. Its range is that for signed and that for unsigned. It's pretty big. Floating point number, its size is 4 bytes. Its range is that. What's this here? Plus minus 1. What is this? What is this saying? I'm not sure what this is saying. Approximately 6 digits of precision. Okay, double. It says it's 8 bytes, and it has 15 digits of precision, and a much bigger range. A long double. Size is usually 80 bits, is introduced in the C99 standard. Andre says, how did you learn computer science? Did you graduate from a college program or something? No, everything I know is just from, not from college, just from learning and doing, I guess. Doing stuff like this. I also have an uncle who's a programmer that I work with, and he's taught me a whole lot. But I'd say, most of this just I learned on my own. Oh, it means that the range is from the negative of this number to the positive of this number. But then why is it like ... to this? That doesn't make any sense. Oh, because this is an incredibly tiny number. I get you. This is a negative exponent. Okay, okay, okay. But does this mean it can't perfectly represent 0? Interesting. Hello, Ivy. First of all, remember that floating points are very rough approximation for the real numbers. For this example, they are more precise near 0 and less precise for big values. This is exactly the reason their range is so great compared even to longs. Depends on if it's complement 2 or something, I'm not sure. Okay. As a consequence, doing floating point arithmetic with values closer to 0 yields more precise results. Finally, in certain contexts, like kernel programming, the floating point arithmetic is not available. As a rule of thumb, avoid it when you do not need it. For example, if your computations can be performed by manipulating a quotient and remainder, calculate by using the percent and modulo operators. You should stick with them, okay. Typecasting. The language allows you to relatively freely convert between types. To do it, you have to write the new type name in parentheses before the expression you want to convert. So you say turn A into a double like that. Okay, you can turn B into a char. Surely this wonderful open world of possibilities is better controlled by your benevolent dictatorship, because these implicit conversions often lead to subtle bugs when an expression is not evaluated to what it should be evaluated. For example, as char is usually signed number in range -128 to 127, the number 129 is too big to fit into this range. The result of an action, shown in listing 9.2, is not described in the language standard, but given how typical processors and compilers function, the result will probably be a negative number, consisting of the same bits as the unsigned representation of 129. What will be the value of k? We don't need to do that. We can pass on. Boolean type. We have already seen that C89 lacks booleans. However, C99 introduced booleans as a type. Underscore bool. Why is it underscore bool? If you include standard bool, you have access to values true and false and the type bool, which is an alias of underscore bool. Oh, okay. The reason behind this is simple. Many existing projects already have boolean type defined for themselves, usually as bool. To prevent naming conflicts, the C99 type for booleans is underscore capital bool. Including the file standard bool signifies that your code is free from any custom bool definitions, and you are picking the one conforming to the standard, but with more humane name. We encourage you to use the alias type bool whenever possible. In the future, the bool type name will probably be declared deprecated, and after several standard versions, it will not be used anymore. Gotcha. Implicit conversions. As a weakly typed language, C allows one to omit cast sometimes, even when using data of different type than intended. When the required numeric type is not equal to the actual type, an implicit conversion is performed, which is called integer promotion. If the type is lesser than an int, it gets promoted to signed int or unsigned int, depending on its initial signed or unsigned nature. Then if they're still different, we climb up the ladder shown here. So from int to unsigned int to long to unsigned long to long long to unsigned long long to float to double to long double. Gotcha. Army Kajkiani. Hey, I see you're looking at C. Are you new to C and low-level programming? I learned some C a long time ago. But yeah, I'm pretty new to low-level programming, I'd say. Most of what I've learned has been in this video series. So if you go back through the playlist, then you'll see pretty much everything I've learned. Remember that long and long double have appeared only in C99. They are, however, supported as language extension by many compilers that do not support C99 yet. The convert to int first rule means that the overflow and lesser types can be handled differently than an int type itself. The example shown in listing 9.3 assumes that size of int equals 4. Okay. In the last line, either x, y, or z is promoted to long because it is not required by standard. The arithmetic will be performed within the int type, and then the result will be converted to long. Gotcha. Be understood. As a rule of thumb, when uncertain, always provide the types explicitly. For example, you can write long x equals long a plus long b plus long c. While the code might seem more verbose after that, it will at least work as intended. Interesting. Let's look at an example shown in listing 9.4. The expression on the third line. Okay, yeah. all of these actually this kind of looks important. The value of I will be converted to float. So this becomes a float. It's added to f, so we have a float, and then it's converted to a double and then stored. Okay. So it's not like you convert both these to doubles and then do the math. You do the math as what they are and then convert it to what this is. Okay. All these operations are not free and are encoded as assembly instructions. It means that whenever you are acting on numbers of different formats, it probably has runtime costs. Try to avoid it, especially in cycles. Pointers. Given a type t, we can always construct a type t star. This new type corresponds to data units which hold address of another entity of type t. As all addresses have the same size, all pointer types have the same size as well. It is specific for architecture, and in our case is 8 bytes wide. Our case being x64, right? Using operands ampersand and star, one can make an address of a variable or dereference a pointer. Look into memory by the address this pointer stores. Listing 9.5 shows an example. Section 254, we discuss a subtle problem. If a pointer is just an address, how do we know the size of a data entity we're trying to read starting from this address? An assembly was straightforward. Either the size could have been deduced based on the fact that two MOV operands should have the same size, or the size should have been explicitly given. For example, move, quad word, array. Yeah. Here, the type system takes care of it. If a pointer is of type int star, we know that dereferencing it produces a value of size of int. Gotcha. Int star px. I think my formatter would do something different, wouldn't it? Like, let's get rid of all this. If I make int x equals 10, and then int star px equals pointer to x. Yeah, mine formats it different. What do you guys like better? Do you like int star px, or do you like int star? I feel like this makes more sense, right? Because this is the type. No? Like, why would this make sense? What do you guys think? Star px is the standard. You like int star more though? Connor, why int star px? Like, what makes this better? Let's do a poll. Int star px or int star px? Stefan, that won't work because if you do int star x, y, only x is a pointer. Oh, that's interesting. Gotcha. Okay, that makes sense. It still feels a little weird because this is the type and this is the value, but oh well. And then we dereference px and make it equal to 42. And then we do some stuff with it. Okay, but that makes sense. When you program in C, pointers are your bread and butter. As long as you do not introduce a pointer to non-existing data, the pointers will serve you right. A special pointer value is 0. When used in pointer context, specifically comparison with 0, 0 signifies a special value for a pointer to nowhere. In place of 0, you can also write null, and you're advised to do so. Null. Oops, not that. Null. Null is just 0. The value is 0. Whoa. It expands to void star 0, a pointer to nothing that is 0. That's interesting. So it's a null pointer. It is a common practice to assign null to the pointers which are not yet initialized with a valid object address, or return null from functions returning an address of something to make the caller aware of an error. If 0 is 0, there are two contexts in which you might use the 0 expression in C. The first context expects just a normal integer number. The second one is a pointer context, when you assign a pointer to 0 or compare it with 0. The second context, 0 does not always mean an integer value with all the bits cleared, but will always be equal to this invalid pointer value. In some architectures, it can be, for example, a value with all bits set. But this code will work no matter the architecture because of this rule. Okay. There is a special kind of pointer type, void star. This is the pointer to any kind of data. C allows us to assign any type of pointer to a variable of type void star. However, this variable cannot be dereferenced. Before we do so, we need to take its value and convert it to a legit pointer type, like int star. A simple cast is used to do this. Okay. You can also pass a pointer of type void star to any function that accepts a pointer to some other type. So it's kind of like an any star or something. Pointers have many purposes, and we are going to list a couple of them. Looks like my poll pretty much decided everybody liked int star px, so I'll end it there. Thank you, people. All right. What? $10, save us? Save us? Save us? How do you say your name? Thank you so much. I really appreciate that, man. This is the first $12. This is the first money I've earned doing any of this. All right, because it binds to the variable, not the type. Take int star a comma b. You'd think both are pointers, but no. A is a pointer, but b is an int. Okay. Yeah. That makes the intention clear. Gotcha. So if I did want to make two pointers, so int, if I did it like this, a comma b, it actually binds to the variable, not the type. That's what you're saying. Okay, so it's really, I do this if I wanted to make two pointers. So then a becomes int star and b becomes an int star. But if I did this, b is an int and a is an int star. Gotcha. Thank you so much. All right. Cool. What should be set here? Okay. You can also pass a pointer of type void star to any function that accepts a pointer to some other type. Pointers have many purposes, and we are going to list a couple of them. Changing a variable created outside of a function, creating and navigating complex data structures like linked lists, calling functions by pointer means calling functions by pointers means that by changing pointer, we switch between different functions being called. This allows for pretty elegant architectural solutions, okay? Pointers are closely tied with arrays, which we discuss in the next section. Here's arrays. In C, an array is a data structure that holds a fixed amount of data of the same type. So to work with an array, we need to know its start, size. We know its start, the size of a single element, why is this? So why do the icons work up here? Oh well, we'll be good. All right, we need to know the start, the size of a single element, and the amount of elements that I can store. Gotcha. Refer to listing 9.7. to see several declarations of array, several variations of array declaration. This array size is computed by the compiler because we're literally doing it raw. This array is initialized with zeros. Its size is 256 bytes. So you initialize it with 32 zeros. And then however many bytes are in a long, I forget, times 32 must be 256. Okay. As the amount of elements should be fixed, it cannot be read from a variable. To allocate memory for such arrays whose dimensions we do not know in advance, memory allocators are used, which are even not always at your disposal. For example, when programming kernels. Gotcha. We will learn to use standard C memory allocator, malloc and free, and we'll even write our own. Oh dear. That sounds fun. You can address elements by index. Indices start from 0. Oh dear. The origins of this solution is in the nature of address space. The 0th element located on an array, starting address plus 0 times the element size. Yes. Listing 9.8 shows an array declaration, 2 reads and 1 write. Yeah, I see indexing like this. Cool. Are we scrapping Rust and Lovely for C? Nope, the operating system is still going to be written in Lovely. I'm just learning C because, one, it was told to me that it'd be a good idea, and two, because pretty much all resources are in C out there. If you look at like OS dev resources, they're mostly in C. So if you think for a bit about the C abstract machine, the arrays are discontinuous memory regions holding the data of the same type. There is no information about type itself or about the array length. It is fully a programmer's responsibility to never address an element outside an allocated array. Whenever you write the allocated array's name, you are actually referring to its address. You can think about it as a constant pointer value. Here's the place where the analogy between assembly labels and variables is the strongest. So in listing 9.8, an expression myArray actually has type int star because it is a pointer to the first array element. Whoa. So if I make an array here, like, how do you make an array? Here we go. Int my array equals, 3, 2, 3, 4. My array. Well, it says int 3. But it really is an int star is what you're saying? If I made a function down here that takes an int star, takes an int star. How do you do this? And then, returns 9. We'll make this int. Then we could say like takes int star. Do I have to declare this thing up here? Now it's happy. Sure enough, it's happy with that. Intriguing. I'm intrigued. It also means that an expression star myArray will be evaluated to its first element, just as myArray 0. Okay. So I could say like int foo equals star myArray. And now foo's an int. Cool. Arrays as function arguments. Let's talk about functions accepting arrays as arguments. Listing 9.9 shows a function returning a first array element, or -1 if the array is empty. Okay. Gotcha. This is interesting. So you have like int. Oh, I have to do this up here. No. Int first. Int array. We don't know the size. What's a size t? It's just an unsized long. Okay. If size is 0, then return -1. Because then there's no first element. Otherwise, return array 0. Or we could do this too, no? Those are equivalent. Wonder if there's any difference in performance or anything. Do you guys know, is there any like preferred way, either for performance or just for semantics or anything, like whether you should do array 0 like this if you're just doing it like that, or whether you should do star array? Is one better than the other? Any thoughts on that? I'll leave it like this because this is maybe a little more clear, like what the intent is, right? All right. Unsurprisingly, the same function can, oh, look at this. That's exactly what I just did. But that's not all. You can actually mix these and use the indexing notation with pointer as shown. What? So I can also make this int star array. And then I could do this. This is nuts. Have to head to work now, but have a good stream. Interesting stuff. Thanks so much, Sebastian. Thank you so much for the super chats. You can actually mix these and use the indexing notation with pointers as shown in listing 911. Yeah, that's what we just did. Compiler immediately demotes constructions such as int array that into the arguments list to a pointer int star array. Okay, and then works with it as such. Syntactically, however, you can still specify the array length as shown in listing 912. Oh, you can do this too. This number indicates that the given array should have at least that many elements. However, the compiler treats it as a commentary and performs no runtime or compile time checks. That's interesting. C99 introduced a special syntax, which corresponds essentially to your promise given to a compiler that the corresponding array will have at least that many elements. It allows the compiler to perform some special optimizations based on this assumption. So you have this little static thing in here. Okay. The designated initializers in array. C99 introduces an interesting way to initialize arrays. It is possible to implicitly initialize an array to default values except for those on several designated positions, for which other values are provided. For example, to initialize an array of 8 int elements to all 0 except for the indices 1 and 5, which will hold values 15 and 29 respectively, the following code might be used. Whoa. That's interesting. Right, so you make it like this. But you can specify this. And you can specify this. Whoa, it even has its value written in here. 0, 15, 0, 0, 0, 29. Hold on a minute. That's not 8. Huh. Because the LSP isn't smart enough to know where it ends. If I make this a 2, this is cool. Exceeds bounds. That's nice. The initialization order is irrelevant. It is often useful to use enum values or characters values as indices. This shows an example. Okay, this is interesting. So I could say like in white space. This is like a map of which ASCII things are white space, right? This is white space. All the others will be zeros. When is this gonna break onto another line? Never. There we go. It sorted it. Does it do this kind of thing where you can kind of like tell it to, and it'll kind of listen? Nope. Enum colors. Red, green, blue, magenta. Gotcha, okay. And then you can end up... Okay, so these end up just being like ordered, right? This is 0, this is 1, this would be 3, this is 4. Cool. Type aliases. You can define your own types using existing types via the typedef keyword. The code shown in listing 915 is creating a new type, myTypeT. It is absolutely equivalent to unsigned short int, except for its name. These two types become fully interchangeable unless later someone changes the typedef. Andre, why are we coding in C? I thought your alias would be built in Rust or the language you created. It will be built in the language I created. I'm learning C because it was recommended to me for one, and also because pretty much all resources out there are in C. So I'm not planning on getting like amazing at it. I just want to do some of it. You can see the suffix T in type names quite often. All names ending with T are reserved by the POSIX standard. POSIX or POSIX? Which one? This way newer standards will be able to introduce new types without the fear of colliding with types in existing projects. So using these type names is discouraged. We will speak about practical naming conventions later. So what are these new types for? Sometimes they improve the ease of code. Yeah, okay, this is easy. All right, a very important example of a type alias is size T. This is a type defined in the language standard. It requires including one of the standard library headers, for example, including standard def. Its purpose is to hold array lengths and array indices. It is usually an alias for unsigned long. Thus, in Intel 64, it typically is an unsigned 8-byte integer. Never use int for array indices. If you are dealing with a poorly designed library, unless you are dealing with a poorly designed library which forces you to use int as an index, always favor size T. I wonder why. Always use types appropriately. Yep. How much longer is this section? Pretty lengthy. What time is it? Where was I? Wait, we were already here. Type it. Okay, so we're here. All right, I might cut this stream a little bit short. I have some stuff to do, and yeah, I think that's probably good for this morning. So, thanks everybody for getting on. Might do some lovely later, but it's pretty unlikely. I'm sort of busy today, which is why I need to stop now. So normally I go a little bit longer. see you all tomorrow morning. I'll do some more of this probably, and potentially this afternoon I'll do some lovely, but I can't promise that. Cool. Thanks everybody.